Hi everyone. In the last video or in the previous video of my entanglement entropy, I talked about this entanglement entropy in quantum mechanics, basic qubit example. Now in this video, I will talk about entanglement entropy in QFT. So we will start with Euclidean time method for quantum field theories. Now Euclidean time is when we map Minkowski time with iota tau. This tau is the Euclidean time. So suppose we have a field phi of x comma t. Now this will be mapped to phi of x tau. This is the field in Euclidean time. Now for getting the entanglement entropy, we first need to calculate the density matrix. And for density matrix, we first need to calculate the global ground state from where we can get the full density matrix, and then we can trace out all the degrees of freedom of the region which is inaccessible to us. So we first need to calculate the global ground state in terms of path integral. So for that, suppose we have a field phi of x0, this is some state, and we can make its time evolution in Euclidean picture. It is h tau, and this gives the state phi of x tau. Okay, now given this information, we can write the path integral as phi x2 tau 2 phi x1 tau 1. This transition amplitude in terms of path integral is proportional to up to some normalization constant d phi and exponential minus se phi. This is our action functional, and that is also Euclidean action. So this is our transition probability amplitude or path integral. Now this quantity can be written as phi of x2 comma 0 and e raised to minus h tau 2 e raised to plus h tau 1 phi of x1 comma 0, and this is the same thing. Now what I have done is I have separated this into this form, right? Exponential h tau 1 on this state will give you this state. So that been done. Now consider a different state, say a chi, such that its overlap with the ground state is non-zero. This is non-zero. So what we want, we need to construct the ground state. So that is what we will do from here. So there is some energy spectrum for the Hamiltonian of the theory. So let these be the basis state, and this will give you En n. Now consider the time evolution of this state. First of all, this state can be written in the expansion in terms of these states, which implies chi is equals to summation over n. Any state in the Hilbert space can be written as some linear combination of the bases, right? Now if we do the time evolution exponential h t of chi, this exponential h t will go inside, and since these states are eigenvectors of h, this will give you summation over n Cn e raised to Ent and chi. Suppose ground state energy is 0, E0 is 0, right? Now in the limit t goes to minus infinity e raised to ht chi, this will be limit t goes to minus infinity Cn e raised to Ent chi. Now in the limit t goes to minus infinity, for all values of n there is a summation n. For all value of n this goes to 0 except for n equals to 0, because e0 is 0 in this term will become 1. So only ground state survives. So this is ground state. So if we want to find the ground state wave function, which is some psi 0 of phi of x, this will be phi of x 0, right? And 0 can be written as in this form. So this will be limit t goes to minus infinity phi of x exponential ht and chi, because exponential ht chi as limit t goes to minus infinity, this is ground state 0. Now we have something similar here, right, in terms of path integral. So if we want to extract the ground state in terms of path integral, what we need to do, so this exponential can be written as exponential h tau 1 minus tau 2, right? So this can act as capital T. Now to extract ground state from here, because this is some function here, this is some function here, t should go to minus infinity to get the ground state wave function, which implies tau 1 minus tau 2 should go to minus infinity. So let tau 1 goes to minus infinity and tau 2 go to 0. What does this imply is the wave function psi 0 ground state wave function in terms of path integral can be written as integral. Now this integral have limits from phi of x1 tau 1 to phi of x2 tau 2. Now since tau 1 is at minus infinity, so the lower limit is phi of x1 comma minus infinity up to some alpha x. So this is function of alpha x, right? So this is proportional to some alpha x, which is phi of x at 0, since tau 2 is 0, and this is a measure exponential minus s Euclidean of phi. So it is like, to get the ground state for any theory, we divide, we have this boundary for, if that is visible, yes. So this is time direction, Euclidean time tau, and if you are in the theory with dimension capital D is equals to d plus 1, then this plus 1 direction is for time tau, and this d are the spatial dimensions, which with and this is one boundary, del v of dimension d minus 1. So the configuration of this boundary is governed by this function alpha x, right? And to get the ground state, we will integrate our path integral in this region. This will give you the ground state. Now from here we can calculate the full density matrix rho as psi 0 star of alpha plus and psi 0 of alpha minus. These alpha plus and alpha minus are same copies of alpha x, and then we can do some manipulations to get to the reduced density matrix. That we can do in any other video. So thank you.